So welcome everyone to the CPM SOC workshop, unfortunately online, obviously, because of the lockdown. So today we'll be going over the problem solving process. What this means is we'll be going over an example problem, the whole process. So from reading the question down to solving it and then coding it up. Then we have a problem set and probably have some time to think about that. And then with half an hour to go or so, we'll go over a second problem. So onto this first problem then. So the problem is called swappable. It's in the problem set, which I'll send the link to once we finish this. So first of all, just go over the problem. So obviously the first part when you're solving a problem is, or the problem statement. And that'll have the information about the problem. So here you're given an array of integers. And the question's fairly simple. You want to count the number of pairs, ij, where ai doesn't equal aj. So the number of pairs of elements that are different. And so problems always have constraints, first of all. So the number of elements is up to 300,000. And each value is up to 1 billion. And they have an example input. So here, and the number of elements. So I've omitted the input format for simplicity, but the input format is the first line is n, the number of elements. So 3 followed by the array. So the question is number of pairs ij where ai doesn't equal aj. The answer is going to be 2. The first pair is this 1, 7 pair here. And the second pair is this 7, 1 pair. So there's going to be 2 pairs. Obviously the 1, 1 does not count because they're the same thing. So the answer should be 2. As another example, if we had the input, let's say 2, 3, 5, 2, 2, and that was obviously n is 5 in this case, then the answer would be, I think there's, well, 1 pair, 2 pairs, 3, 4, 5. If I can count correctly, there's 6 pairs where the elements are different. Okay, so when solving the problem, so we have in this case that ends up to 300,000, and the time limit for this problem is a second. And so in order to have a solution that's fast enough, it can't use too many operations. So in general, you can assume about 100 million operations per second. And so for those of you who've done a course that teaches time complexity, then you know that you have to do this in about order n log n, but not order n squared. But I'll explain, if you don't know what that means, I'll explain why that is too slow when going over this first solution. So the first solution is the obvious solution. We just have 2 nested for loops and consider each pair of elements. So our first for loop loops over the array, second for loop loops over the array, and we just check if ai and aj are different, add 1. Essentially just doing what the problem asks you to do, the most simple solution. The problem of this, think about number of operations, it's doing n squared work. N is up to 300,000. So 300,000 squared is this large number here, if I did it right, 90 billion. That's much more than our 100 million. 100 million is like 8 zeros, I think. This has 10 zeros. So it's about 900 times slower than what we can do in a second. So this will take maybe, 10 minutes to run or something like that, which is way too slow. So this solution, while good, is too slow. In some competitions, you get partial marks for this solution. In the case of this problem, you won't, but yeah. So we'll quickly code up this solution just for example's sake, just to show you how you do this and why it'll get timeout. So if I just quickly share my other screen. Here. So we're going to use C++, but in fact it's very simple to see. It'll look essentially the same as C. So C standard IO, this is just the same as stdio.h in C. That's just to get input. And so our solution looks like, well, we scan in n. Again, we're going to use scanf. Then we have our answer. And we're going to have our array. So declare this globally and our array A up to 300,000 long. And then we're just going to scan in the input. And then we're going to 2 nested for loops. So the first for loop goes from 0 to n. The second for loop goes from I plus 1 to n. And we're just going to go if these elements are different, add 1 to our answer. And then we just print our answer at the end. It's a very simple solution. Let's compile it and run it. So here I have the first sample input. The problem had some more examples. So in this case, the correct answer is 45. So we run our code here and we should get 45. And here we should get 173. And we see, yeah, that'll work. So our solution is accurate. But now let's submit it and see how it goes. So we're going to use a judge called VJudge here. So it's got a problem statement here. It's the same thing. It just has some more details like the input format. But to submit, obviously just press submit. We're going to copy and paste our solution into here. We got C++. And then we'll just submit this. And hopefully it won't take too long. And we see it got time limit exceeded. So the solution was just too slow. Yeah, because of the fact that this is n squared solution, so the number of operations will be quite large when n is 300,000. And yeah, unfortunately, we don't get partial marks, but it's worth our exercise anyway. So now back to the slides again. This solution is too slow, so we need to come up with a better solution. I'll give all of you a few minutes to think about it. And if you have any ideas on how to improve this, put it in the chat. Otherwise, I'll go and I'll explain the solution. So we'll give until 1:15, so 3 minutes to think about any solutions. Oh yeah, and as Jeffrey put in the chat, forgot to mention this, but yeah, feel free to ask any questions you have. Either just chat or unmute and talk. So, yeah, I'll just go back to the statement so you can read the problem in case you've forgotten it. Here's the question. Give 30 more seconds. Dallas, what's your genius idea? All right, so feel free to share any more, but otherwise I'm just going to go on. Next idea. FFT. See, I'll let you code that up. Maybe you can explain code it up and see who can get it faster. Anyway, so the problem asks us to count number of pairs where elements are different. But what if instead we count number of pairs where elements are the same? Because that might be a bit easier. And in fact, it's a very similar thing, because the answer, so let's say the number of things that are the same, number of pairs that are the same is x. Then the answer to the original problem is just n choose 2 minus x. And like as an example, in the sample input, so we had as our example input at earlier, we had 171. Then in fact, there's going to be one pair of that they're the same. These two ones here. These are the same. Overall, there are 3 possible pairs. And so the number of pairs that are different is just 3 minus 1 is equal to 2. So we just, instead of counting number of pairs that are different, we count the number that are the same. And then we just go n choose 2. That's this number here, the number of pairs, minus the number that are the same. And that gives us our answer. But we might be wondering why count the number of pairs that are the same? Because this seems like it's going to be a bit easier. And in fact, it is. The reason why is if we know how many elements of each number there are, we can do this count, the number of pairs that are the same. In particular, let's call Cj the number of elements where like ai is equal to j. So for example, in this original problem, in this sample input, sorry, we had 171. We would have C1 or C1 is equal to 2. There are 2 elements with value 1. C7 would be 1. There's 1 element with value 7. And C of everything else, so like C of 5 would be 0, for example. There's nothing that's a 5. Then the number of elements that are the same is just, well, we have 2 choose 2 here. So we have 2 choose, because we have 2 elements with 1. So 2 choose 2 will be the number of pairs of 1s that are the same, which is equal to 1. Here we have 1 choose 2, which is 0, and 0 choose 2. As a bigger example, let's say we had the input case 5, 1, 1, 2, 7, let's say 1, 2, 1, 2, 2, 3, 4. In this case, we have C1 is equal to 2, C2 is equal to 3, changes C3. Oh, change this. C3 is equal to, so C2 is equal to 4, C3 is equal to 1, and C everything else equal to 0. Then the number of pairs that are the same is going to be 2 choose 2 from this. So 2 choose 2 is equal to 1, and then 4 choose 2, which is going to be 6, I think. 4 choose 2 is 6. Correct me if I'm wrong. That's just 4 times 3, 12 divided by 2. And then we have 1 choose 2, which is 0. So the number of pairs are the same is just 1 plus 6 plus 0 equals 7. So to find the overall answer to this test case, so we have x equals 7. Then we take 7 choose 2, number of total pairs. So 7 choose 2 is 7 times 6 divided by 2, which will get us 21. So 7 choose 2 is 21. And so we're going to go 21 take 7, which is our final answer of 14. So this gets our answer. So now our new problem is just, we want to count for each value, how many elements have that value. So we want to look out for each value, how many elements have that value. So to find this CJ, one way of doing that is just to sort the array. So notice, so before we had the input like 2, 1, 2, 2, 1, 3, 2 or something like that. If we sort that array, we get 1, 1, 2, 2, 2, 2, 3. Once the array is in sorted order, it's pretty easy to count how many of each element there are. We can just do one for loop to count that. Once we can do that, we now have this CJ. Then for each CJ, we just count the value choose 2 using this formula here, which fairly well-known math Probably well-known formula and pretty easy to derive. So the time complexity of sort is order n log n. For those of you who have done a course where that's taught, 2521 maybe, I can't remember. Either way, just take this as granted for now. And then the rest of it's order n. We're just doing one for loop. So the overall complexity, time complexity, is order n log n, which is fast enough for our solution to run in time. And so that's the solution. If there aren't any questions, I'll code it up. And also in the meantime, fill out the attendance form as well that Jeffrey put in the chat. Gets us the ARC dollars, probably, I hope. I actually don't know. Do we get money for online events?
Yeah, we're supposed to, but like ARC is very slow.
Oh, okay. Support us and go in the draw to win a free pizza. All right. So here is we're going to code up the faster solution. Again, using C++. We're going to have to include algorithm. This will give us access to a built-in sort function, which is nice. So our new solution is we start off by scanning the input again. We then sort the array. So on C++, if we go standard sort and just give the array plus n, this will just sort the array. It's a nice inbuilt function. So now we have the array in sorted order. Next thing, we want to compute how many of each value there are. So we're looking for contiguous. So our array could be like 1, 1, 2, 2, 4, 4, 5. Looking for contiguous things with the same value. So to do that, we can just keep track of the current run. So let's say current length is equal to, we'll say 1. This corresponds to just the first element in the array. And then for each other element, so we're going to say, first of all, we're going to check, is this value the same as the previous value? So if this element here is the same as the previous one, we're going to increase our current length. So the current amount, we're going to increase that by 1. Otherwise, if the values are different, then we've finished our run of, say, 1s, for example, and this will count the number of 1s. So then to our answer, we're going to add to our answer this choose 2, which is just going to be current length times current length minus 1 divided by 2. That's the choose 2 formula. And we're going to set current length to 0 to reset our run. Then our answer is just going to be equal to, in fact, n choose 2 minus the answer. So we're going to go n choose 2 here minus the current answer, like this. And that is just the formula we described before. So here we're computing all the runs and we're going to print the answer. So we run this on, let's in fact run it on this sample input here. He gets 2. What about another case? Say 1, 2, 2. Should be 2 as well. Yep, seems to be. I'm running the wrong code, that's why. I'm running the wrong solution. Never mind that. Let's compile the correct one. Still correct. Run it on this new case. 1, 2, 2. And it's getting the answer of 3, when in fact the answer should be 2, because these cases should be identical. So there's obviously a bug somewhere in our code. So testing on a few symbol cases is good, and we've detected a bug. So in order to debug this, let's just print out at the end. I'm just going to print, using classic printf debugging, the answer at this point. And in fact, our thing is saying that there's 0 pairs of elements that are the same. The reason for this is we only trigger this else statement here if an element is different from the previous element. But the problem is, let's say our input in this case is 1, 2, 2. it won't be triggered for this last run here because there's nothing after it to trigger it. So there's a few ways of doing it. One way is to add a statement at the end here. We can go, in fact, let's do this. We can just trigger the last one here by just doing this. We're just gonna say, okay, make sure we count the last one as well by adding one final check here. So this will add the last one, and we can recompile that, and we should now, we're still getting the wrong answer. Interesting. Let's just print out the current length here. The current length is 1. Oh, in fact, we should set current length to 1 here, not 0. That is because, let's say we have this case here. We trigger this else statement here, at which point we already have 1, 2, which is why we have similar idea why we have this current length of 1 here. We set it to 1 again here. And so now our code passes this case. Then we will check our code on the other cases. So back on the original case here, the correct answer should be 2 to this case. We check our code. It gets 2. We should get 173 to this case here. And we get that, and we should get 45 here. Our code is passing all of these cases. The next thing is to submit it. We're going to share screen again. Our old submission. And copy our code in. And submit. Waiting for judge. And code is getting wrong answer. Now, our code's passing our sample cases, which are fairly comprehensive. There's some fairly large ones, but it's getting wrong answer. Now, the first thing I recommend you think about when you get wrong answer is integer overflow, because that's a common cause of error. So in this case, what is the maximum possible answer? Well, if n was equal to 300,000 and every value was different, the answer would be 300,000 choose 2, which is 300,000 times 290,000, 200 divided by 2, which is about, I got about 4.5, if I did maths right, 4.5 times 10 to the power of 10. That is the biggest possible answer, is this value here. But for those of you who are aware of the maximum value in can store, I think that's in 1521, I think. So if you've done 1521, you should know that a 32-bit integer signed into can store values up to 2 to the power of 31, which is about 2 billion. So 2 times 10 to the power of 9. So an int variable can only store up to 2 times 10 to the 9, but our answer could be bigger than that. So it could overflow. So you use a long variable. So a long in C and C++ can store up to 2 to the 61, which is around 10 to the power of 18. I think 4 times 10 to the power of 18, or maybe even 8 times 10 to the power of 18. Something like that, which is going to be big enough for essentially every problem in competitive programming. There is very rarely a case where this is not enough. Problems are designed so that longs will be enough for you. So instead of typing long everywhere, we can go type def long LL. This means you can use LL instead of long. Just change stuff to longs. %LOD is scanf for long. So we're going to change our stuff to longs. Just the stuff that matters. So answer, and then print long here. And this hopefully, so our code first of all should compile to get the correct answer, but now it's using longs instead. And so it should pass, hopefully. So again, we can submit our updated code. And in fact, our code passes. It says accepted here. So it's 14 out of 14. So it's passed all the test cases. So generally in competitive programming, you have to pass all the test cases. Some problems are different, but normally to get the point, you've got to pass every test case. And that green accepted means we did. And we did fast enough. So that's this problem solved. Are there any questions about that? If not, I'm going to do a quick tour of VJudge. So VJudge is a judge you can use to submit problems, which we've just used. Again, submitting is fairly easy. In fact, VJudge isn't really its own judge. It just leeches off other judges. So this problem originally is from @Coder, which is a competitive programming website. And the problem's here. I'll get that problem in a second. The question in a second, sorry. And so, yeah. So we've got a number of problems from different sources here. The question of how much do you care about how long the division, modification, etc. takes? For all intents and purposes, you can kind of assume it's constant. We generally when we're computing complexity, we assume that multiplication, division, etc. is a constant operation, just because that's a nice approximation to make. And generally, computers are pretty optimized that they can do multiplication pretty quickly and things like that. Multiplication, division are fairly fast on modern computers. There is one thing. Generally, a long will be a little bit slower than an int. So because it's a bigger value. In most cases, this doesn't matter. Normally, if you have the correct solution, it should easily pass. It's not normal that the correct solution is a squeeze. So normally, like if we look here, our solution passed. The slowest case was 59 milliseconds, but the time limit was like 1 second or something. That's like 20 times faster than it needs to be, because the correct solution will always easily pass. And when I'm using my 100 million figure of operations in a second, that's essentially assuming that addition, multiplication, division, they're just one operation. Some operations are slower. I think modulo, for example, is generally a bit slower because that involves like a few different things going on, like a division and multiplication, I think. But yeah, generally, you don't have to worry about those speeds. So back to VJudge. So each week we have a problem set. So we have 4 problems in a set, plus this problem here. They're approximately in difficulty order, except swappable is not in order. So we recommend that you have a go at these. The first problem here should be very easy to do. The point of this question is just to get you familiar with submitting. So submitting is pretty easy. Just submit, copy your code in here, and you're done. And we have problems that get kind of harder as you go along. And so for the next bit of time, we're just going to recommend that you work on this, and then we'll reconvene at 1:30. So in an hour? No, we'll go 1:15. We convene at 1:15. So in 40 minutes, at which point we'll go over one of the solutions to one of these problems. All right. So going to go over problem D from the set. So I'll just quickly share my screen with that. So I'll just give you like 30 seconds to have a look over it, and then I'll also explain it. Okay, so in this problem, you're given a string, so a number of characters, and you're told that a string is unbalanced if its length is at least 2 and more than half of the letters are the same. So the examples I give are Voodoo and Melee, because Voodoo has 4 out of 6 characters are O's, and Melee 3 out of 5 are E's. Noon is not, because only 2 out of 4 are N's or O's. And also A is not, because it's only 1 letter long, and you need to be at least 2 letters long. So, no. So you're given a string of lowercase letters. You want to determine if there exists a substring that is balanced, a contiguous substring that is unbalanced. So a range of characters where a majority of them are the same letter. And if that's true, you want to show such a substring. So if the answer is positive, if the answer is yes, you want to show such a substring. So for example, this case here, needed, they said from character 2 to character 5 is such an unbalanced substring, which is true. Also from character 2 to character 3 would also be a valid answer, or even from character 3 to character 5. That'd be EDE. They're all possible answers. So, and 2, 6. So there's quite a few possible answers. You just have to output an answer. In the case of @coda, there is no unbalanced substring. So you output -1, -1, which just indicates the answer is no. So the bounds for the problem are, so for full marks, up to 100,000 characters in the string. So your string has at most 100,000 characters in it. However, for partial marks, so 200 points out of, I'm not sure what it's out of a total of. That's, I don't know, 20%, let's say. 20% of point, for 20% of points, you have n is up to 100. Up to 100 characters in the string. So you can get partial marks for a slower solution. So I guess very quickly, what's a very naive solution? Well, there's an order n cubed solution. We'll just go, let's even solve an n cube. We'll go in order. We'll have a order n cube. So we fix the range and consider each. So we have our string. Like, what's the example input? They give needed. So we have our example string needed. And you try every range of it. So for example, you try the whole thing. And you want to work out if one character has the majority. So to do that, you can just count the occurrence of all 26 letters. There are 26 letters in the lowercase alphabet. So you have an order n cubed times 26 solution. For each range, there's n squared ranges. You count how many letters are in it using like a for loop, for example. And then just check if any one of them is the majority. So order n cubed times 26. This will probably get partial points. So again, just to explain the slow solution, I'm going to very quickly code that up. So this is the input again. And so it's going to scan in the string. So we can store a string as a C style string works. So an array of characters. So we can hash include C string. This is string.h if you've used C before. So we have our string, then kind of 1,000. We can scan it in, scanf%s, our string. We can go, the length of the string is strlen. This is a function that's in C in here, in C++ as well. So just length of the string. Our solution is just for each range, so for each I, for each j, we're going to consider the range I to j and count for each letter how many times it appears. So to do that, let's have an array, a frequency array. Just going to store for each letter. And we're just going to go characters. We're going to initialize this way. So characters from A, you can do in C and also in C++. Because characters correspond to ASCII numbers, so lowercase a is just a number, you can do a for loop over the letters, which is nice. like this. And you can use letters as array indices. So it's going to say the frequency of letter C is 0. It's going to say for each letter, we initialize the count of that variable. So we're going to say, okay, each variable occurs 0 times. We're then going to go for each element in this range. So k iterates over the entire range. I'm just going to say the frequency of this character, we're going to add 1 to it. So now our frequency array will store how many times each character appears. And now we just want to check for each letter, if the frequency of this letter is bigger than the size of the range, j divided by 2. So this should be plus 1 on 2 because of inclusive exclusive. So if this is bigger than the half the size of the range, we're going to print our range. We're going to print, and we're going to add 1 because of we started our arrays at 0, but in the problem they started at 1. So we can go I plus 1, j plus 1, and then return 0 to finish. And finally, if we don't find anything, we're going to print -1, -1. So we compile this code. It compiles. So example input 1 was needed. Our code outputs 1, 3. That is the first 3 things. That's an unbalanced range, so we're good. Second example was just at coda. Our code outputs -1, -1 because there is no unbalanced substring. So we can now submit this code. So we can go submit. It's judging. Getting wrong answer. So wrong answer. And I realized my error. My error is the ASCII for lowercase z could be more than 100. So make this array 200. Basically, the ASCII for lowercase z is 122, I think. And so we're actually overflowing this array here. So we change this to a 200 here. That should hopefully be a bit more correct now. It's judging. Time limit exceeded, but hopefully gets partial points. But yeah, overall it's time limit exceeded. My status. Not sure how it would tell me that. But yeah. So that's solution's too slow, but it should get partial points. We can do an n-squared solution that also exists. I'm not going to go over that because probably not worth the time, but there is an n-squared solution. But we're going to explain a faster solution. We can in fact do an order n solution. To do that, we just need to make observations of what the solution looks like. So consider some unbalanced substring. So we have, let's say the melee, it's an unbalanced substring. And in this case, the letter that occurs the most is the letter E here. But the first letter is an M. So if we got rid of M and just considered this new substring here, this is obviously also going to be an unbalanced substring. Because all we've done is decrease the total number of letters, but we haven't increased the majority letter. So if we have any unbalanced substring, so another one is voodoo, for example, and O is the majority letter, we might as well prune down the ends so that the word starts and ends with the same letter. That is the letter that occurs the most. If we had like voodoo with a V on the end, this is still a unbalanced substring because O occurs 4 out of 7 times. But if we got rid of these two V's at the end, O would now occur 4 out of 5 times and it's still unbalanced. So this proves that there always exists some unbalanced substring that both starts and ends with the same letter. Does that idea make sense? We've now worked out, we've made an observation which reduces the possible answers. Because we just need to find one unbalanced substring. Now we just need to look at strings that start and end with the same letter. But in fact, we can go even better than that. Let's make some more observations. Because, okay, both these examples here, both these examples consist of substrings of size 2 that have the same letter twice. Because if you ever have like 2 O's in a row or 2 E's in a row, this is all already unbalanced. We're done already. And both these examples have substrings that have 2 letters in a row. So one thing to wonder is, well, and needed also has that. So needed also has 2 E's in a row. So one question you may ask is, does any unbalanced substring always have 2 letters in a row that are unbalanced? Well, anyone think yes or no? And if no, do you have a breaking case? So type in the chat if you have an example of a case where this breaks, where there is a string that has an unbalanced substring, but doesn't ever have 2 letters in a row. Or if you think that it's always true. Okay, or no. So a breaking case is here. We have 3 letters in a row, where the first one and the last one are the same, but the middle one's different. So this is a breaking case. This one, yeah, is an unbalanced substring, but doesn't have 2 things in a row. But this one here is of size 3. Okay, another question. Let's consider, for now, just even length strings. So consider an even length unbalanced string. If there is an even length unbalanced string, will it always have 2 characters in a row that are the same? Let's assume that it doesn't. If there's an even length string, so string of length 6, for example, that is unbalanced. That must mean 4 out of 6 of them are the same letter, at least. But the most we can have, so let's say the multiplicator is A. Let's say we have like A, B, A, B, A, B. In this case, we've squeezed the most A's we can without any 2 being next to each other. But we still can only fit 3. Another way of thinking about it is, if you have 6 characters, we can divide this into buckets of size 2. So we have 3 buckets of size 2, like this. If we ever put 2 characters in the same bucket, then we'll have 2 adjacent characters that are the same. But there's only 3 buckets. So in order to have 4 characters that are the same, there must be 2 in the same bucket, and so there must be 2 next to each other. So in any even length unbalanced substring, there will always be 2 characters next to each other that are the same. So yeah, for example, you need like AB, AA, BA, for example, to have 4 out of 6 characters be the same. If you can get exactly half being A's without anything being next to each other, let's replace it with C, for example. In this case, 3 out of 6 characters are A's, but to get 4 out of 6, you need 2 characters that are next to each other that are the same. Okay, but we have this breaking case here. Oh no, which means that there are odd length cases where this breaks. But let's now consider the odd case. So in the odd case, if we don't have 2 characters next to each other, then the only case is we have like A, B, A, B, A, B, A, for example. So 1, 2, 3, 4, 5, 6, 7. So if we have an odd length thing, we can break it up into like buckets like this again. So break into buckets again. Yellow is not a green, let's say. Break into buckets again, except the last bucket is of size 1. Now, if we have 2 things in the same bucket, then we'll always have that there are 2 letters next to each other that are the same thing, which means we can't have that. which means we must have exactly one, let's say A, in each bucket for the majority of characters to be in A. If there's an A in each bucket, that means the last letter must be an A, which means the third from last letter must be an A, etc. Which means the only case where you have a majority of A's in an odd length string where no two A's are next to each other is where you go like A, B, A, B, A, B, where the first and last letter are A's and everything else in between is alternating between A and not A. Another case would be, it could be like B, C, B, A, B, F, B, for example. You have A, B again. You have 9 characters where 5 out of 9 are B's and no two are next to each other. But in this case, the last character is always the majority character. And that's always the same as this one here, which means in any case where you have an odd number of characters where it's unbalanced and no two things are next to each other, you always have 3 characters where the first and the last are the same. So this means if there isn't a substring of size 2 that's unbalanced, there must be one of size 3 that is unbalanced. So if there's an unbalanced substring, there's always one of length 2 or 3. You never need to get any longer than 2 or 3. There will always be an answer of size 2 or an answer of size 3. Does that proof make sense? So we've essentially proven that there is a valid answer of length 2 or 3 if there is any valid answer at all. And this makes our solution a lot easier. Our new solution is just to check all substrings of size 2 and all substrings of size 3. There are linear of these, there are order n of these, so our solution is much faster. In fact, our code can just go check if any 2 elements adjacent are the same, or check if any 2 elements with one gap between them are the same. If yes, the answer is yes. If no, the answer is no. So now we've reduced down our n cubed solution, which can be n squared, but we've reduced it down to an order n solution. So we now have a much better solution. So I'm going to modify our code so that it passes that solution as well. So let's say order n solution. Don't need this anymore. We're just scanning our string. We're going to check. First of all, we're going to check substrings of size 2. Yeah, that's exactly what we need to check essentially. So we're just going to go if AI is equal to AI plus 1, we're going to do 2 for loops. You can do it 1 for loop if you want. We're just going to print. Remember, we're off by 1 index again, so I plus 1, I plus 2, and then return 0. Otherwise, we're going to go to n minus 2. This is because the last 2 things can't be the start of a substring of size 3. So we check substrings of size 3, and we're just going to go this, then you print this. And that is the solution. So by making some observations about what the optimal answer can look like, it's called string, not A. That's my bad. Making observations about what the optimal answer looks like, we can come up with a much faster solution. And so we're outputting, if we look at needed, for example, our code outputs 2, 3. If we look at oh no, our code outputs 1, 3. So our code appears to work. Let's submit this. Where's my code? Submit. Code judging, and it got accepted 24 out of 24. Nice.